This video discusses why monitoring is important, and what parameters must be monitored. It is now exactly 33 years since the first battery monitor was introduced. In fact, our original patent has expired. The first monitor was primarily designed to reduce maintenance hours and replace inexperienced maintenance personnel. Since those early days, a lot more has been learned about why and how batteries fail, and a whole new set of battery problems has arrived with the introduction of VRLA batteries. Today, it has become obvious to users that battery performance cannot be taken for granted. The cost of failures makes the cost of monitoring seem insignificant, especially in large data center applications where even a momentary power glitch to the computers can equate to many millions of dollars in losses. Why monitoring is necessary? There are many arguments for monitoring, but the most obvious reasons are: 1. Increased system reliability. 2. Cost savings from reduced maintenance hours and optimized battery life that justifies initial investments. 3. Personnel safety. Increasing system reliability by eliminating power outages is obviously a huge cost saving. Sometimes, spending money to save money is a tough argument to prove to company accountants, but when the cost of failure is compared to the cost of monitoring, it almost seems irresponsible not to consider it. How can monitoring improve system reliability? Monitoring improves system reliability by detecting battery problems at an early stage, before they can cause an abrupt system failure. How are problems detected? Problems are detected by measuring the internal resistance of each cell or module in the system. The resistance of a cell has been proven to be a reliable indicator of a battery's state of health. The only other method for testing a battery's condition is to perform a capacity test. No one can argue the effectiveness of a capacity test, but, unfortunately, because of its cost to perform, many users will not load test their batteries. The chief advantage of a resistance test is that it can be performed automatically, without any test personnel present. Cost savings. There are 3 ways that monitoring can provide cost savings that readily offset the initial cost of purchasing a monitor system: by reducing maintenance time, by optimizing battery life, and by reducing test costs. The time required to maintain the batteries in a typical small UPS battery cabinet, small telephone office, or power company substation, in accordance with IEEE standards, is at least 25 hours a year. Most of these hours can be saved by using a monitor, and the hours saved will pay for a top-of-the-line battery monitor in 2 to 4 years. Battery life is greatly affected by ambient temperature, excessive cycling, and float voltage. Many users only obtain 50% to 80% of the realistic life of their batteries. Every new battery system must be acceptance tested with a capacity test to prove that it will be able to perform when needed. A permanently installed monitor that can log data during a scheduled or unscheduled discharge eliminates a substantial amount of these costs. If the monitor identifies a problem, then the battery may have to be accessed by maintenance personnel. In the case of a problem, however, the battery will typically be disconnected from the load and the charger, thus reducing the exposure. UPS systems that have batteries installed in a cabinet are especially hazardous to work with, since there is very little space to access the battery terminals for routine maintenance measurements. Some battery parameters are monitored to verify the battery is being operated in an environment that guarantees optimum life, and some are monitored to track the state of health of the battery. For a monitor to achieve its main objectives, it must, as a minimum, monitor the following parameters. 1. Overall string voltage. 1. To verify the charger has been set correctly and is operating properly. 2. Cell voltages. 2. To verify all cells are charging correctly. 3. Ambient temperature. 3. To verify the temperature environment is at or near optimum temperature for long life and maximum capacity. 4. Internal cell resistance. 4. To verify the state of health by identifying low-capacity cells. 5. Intercell resistance. 5. To check the conduction path integrity and avoid possible fires and abrupt shutdowns. 6. Load cycles. 6. To check the number and depth of discharges. 6. This information is used to project battery life and settle warranty issues. 6. Other parameters that are useful in analyzing battery performance are 7. The current delivered by the battery during a discharge is used to calculate the capacity of the battery. 7. It is also useful in parallel string applications to see how the strings share the load. 8. Float current. 8. The float current drawn by a battery can be useful in VRLA batteries to detect thermal runaway conditions. Why batteries fail? It should be noted that all lead-acid batteries have a limited useful life. The normal failure mode that dictates the end of life of a well-maintained flooded battery is positive grid corrosion. The positive grids lose their mechanical strength and start to break apart. Sometimes before this happens, the grid structure has grown to a point where the paste or active material has lost a lot of contact with the grid. Both problems lead to large increases in internal resistance that can easily be detected. The normal life of a good quality flooded battery is 20 years. The most common problem for their early demise has been a drying out or loss of water in the electrolyte. There are also investigations that indicate that secondary reactions from internal recombination of hydrogen and oxygen gases may be adversely affecting the polarization voltage of the negative plates and/or accelerating positive grid corrosion. Both problems lead to a loss of capacity. Failure analysis. Excessive cycling. The cycling capability of a lead-calcium battery depends on the depth of discharge. For example, the battery is only capable of 50 deep cycles, the removal of more than 80% of energy, but can deliver 300 cycles for a 25% depth of discharge cycle. A UPS battery, which normally only delivers about 25% of its stored energy during its 15-minute rated reserve time, can deliver 300 such cycles. Low float voltage. High float voltage. Low temperature. High temperature. This causes loss of battery life.